Welcome everyone from the Crystal Clear Electronics studio. This is a practice-oriented electronics study material in video form, but also available as a free, downloadable, written material from our website. Today we are moving forward with the second season of Crystal Clear Electronics. This is chapter 16. The written material was created by Gábor Kalmár and proofread by Gergely Lágler. Today's presenter is Szabolcs Pályár, whom you may already know from the previous episodes. I am András Bácsi.
Welcome everybody. In this chapter, we will learn about the real-time clock. You will see when and where it is necessary, and by the end of the chapter, you will understand how it works. The real-time clock, or RTC, as we will refer to it later, is a very useful peripheral in a number of ways. We use it in several embedded electronics applications.
Let's first start with the name, which tells us what an RTC really is. This acronym means real-time clock. It is called a real-time clock because it measures time in human form, so an RTC is nothing more than an electronic device for measuring time in the everyday sense, which in most cases is supplemented by a calendar function and the possibility to attach a backup power supply, which is a useful addition if your system is not always on or if you expect the power to be interrupted from time to time.
Generally speaking, RTC can measure time accurately over a longer time period. In contrast, conventional timer peripherals are more inaccurate and can be used to measure shorter intervals. And now it is time to sit down and see these topics in greater detail.
Let's see. In general, RTC is needed in almost every situation where you need to know the exact time. Let's look at some concrete examples, the first of which is a time measurement.
In the most obvious cases, we're thinking of those where we see some form of accurate time on our system's user interface. For example, PC, smartphone, smartwatch, digital alarm clock, household appliances like microwave or the oven, TV, set-top box, etc. The list could go on and on. However, there may also be cases where the time is only used as additional information to the main functionality. In these cases too, the presence of the RTC is essential. The most striking example is the operation of a file system where the creation, modification, and even the access time of files is stored. Another typical use is logging, where it's almost mandatory to save the exact time of the event for each entry.
RTC can also be used for timing the reading of values at the inputs and the writing of the outputs. This is also a commonly used way of using the real-time clock.
Yes, we can choose periodic, single, or multiple timings depending on the task, and there are many examples. Just think of the fact that most household appliances have timer functions, from washing machines to ovens or even TVs. The most obvious example is the alarm clock, where you can set multiple alarms, even customize the duration of the snooze. Or, take the example of personal computers, where you can set the RTC of your PC in the BIOS, so you can turn on or wake up your computer at a specific time. Timing is also important in measuring equipment. Just imagine an air quality monitoring station which has the task to measure and transmit data every 10 minutes.
That being said, let's talk a little about the different forms that RTC can take in each system. For example, in an older microcontroller, there was no hardware unit dedicated to the RTC task, so in one of my previous projects, I found the best solution was to add an RTC IC communicating via an I2C bus to the microcontroller. One such example is the DS1307 integrated circuit mentioned in the Britain curriculum. In this case, the IC did the accurate timing, and I could retrieve the information I needed via the I2C.
Yes, and also the written material mentions another opportunity to solve the assignment in software without a dedicated hardware unit more or less accurate. We're mostly aware of the fact that modern microcontrollers are basically miniature computers, providing integrated solutions for most tasks. This is no different for the STM32F446ZE on the Nucleo board, or F446 for short. The RTC unit is found inside the microcontroller, which means that you can simply just use it only with a minimal amount of additional components connected to the microcontroller. In the following, the introduction and use of this unit will be discussed in detail.
Let's put the RTC peripheral of the F446 into use, for which we need to decide two things in advance. The first is the choice of the clock signal, because the RTC needs a basic clock signal, which is understandable because the RTC is kind of a timer module which can be driven from an external quartz crystal oscillator or from an internal source. On the development board, the first type, an external quartz crystal oscillator, has been incorporated. The other issue to be decided is the use of a backup power supply, which is an optional feature but worth using. The board used in the written material contains this additional element, but in the case of the Nucleo, the user needs to build it additionally to the board.
A backup power supply can come in handy for a watch. It allows you to keep the RTC active if the main power supply to the IC fails, so that your system does not forget the time. The controller we are using has an input pin labeled VBAT, to which a power supply of between 1.65 volts and 3.6 volts must be connected. There are several options to choose from, such as a battery, an accumulator, or a capacitor can take this role. Let's take a look at each of these options. Very often, we find non-rechargeable lithium-based pattern cells, including batteries marked with CR and BR, as a backup power source due to their high energy density and low self-discharge. Batteries can also be used as a backup energy source in several different designs. The most common are the button cell-sized lithium batteries marked with ml and nickel-cadmium or nickel-metal hybrid batteries assembled from a few cells in series. For these small batteries, it is also necessary to use a charging circuit, which in turn adds to the cost. A disadvantage can be the limited number of charge cycles, which means you need to pay attention to battery aging, especially if you have to expect frequent power cuts. Their use may be advantageous if you want to provide power to other circuit elements in addition to the RTC, because in this case, you can benefit from the extra capacity that batteries can provide more easily, even over longer time intervals. Finally, we can also use a capacitor, which is maintenance-free but requires a relatively simple charging circuit. Compared with batteries and accumulators, we can only handle power outages of a much more limited duration, but in return, they are easy to install and there are fewer regulations on the transport and disposal of the chemicals they contain.
We have now chosen a capacitor-based solution. However, before using it, let's take a look at the relevant part of the development board.
The Nucleo panels have the VBAT input connected to the power supply by default, so that the RTC can be tested without an external backup power supply. This is also shown on the second page of the schematics of the development panel, but is also referred to in Table 12 of the user manual. In order to be able to connect our backup power source, which is the capacitor, this connection must first be disconnected. Fortunately, the manufacturer has thought of this also. They've managed to implement this connection with a 0 ohm resistor, which is marked SB156. The abbreviation SB comes from the word solder bridge. This resistor, which is located on the bottom of the panel, can be soldered off the panel with a little manual dexterity. Once removed, we have to take care of powering the VBAT leg. Let's have a look at the capacitor wiring. The VBAT is only an input to the microcontroller, so it cannot charge the capacitor, therefore we must charge it from the main power line. If we simply connected the primary power source to the capacitor, in the event of a power failure, the capacitor would supply power to other circuit elements in addition to the RTC peripheral and would consequently drain very quickly. To counteract this, a diode must be inserted which allows current to flow in only one direction, so that when the main power line is live, the VBAT is powered through the diode and the capacitor is charging, but if the main power supply is lost, the electrical charge stored in the capacitor supplies the VBAT input, and the diode prevents this charge from rapidly dissipating through the main power line. The chosen 0.22 farad capacitor can power the clock for a few days. In the wiring diagram, the capacitor is indicated by the framed part. The capacitance of the capacitor is very high, so that when voltage is turned on, it would cause a very high current to flow, which should be tried to be prevented. This could be avoided by using a current limiting series resistor, but as the capacitor we have chosen has a relatively high internal resistance, this is not necessary. This is pointed out in the wiring diagram.
The VBAT leg of the microcontroller is routed to leg 33 on the CN11 connector on the panel. This can be read from table 21 in the board's user manual. On our panel, this connector is not placed, so we solder this red wire here to connect the capacitor.
There are three ways to provide a clock signal to the RTC peripheral. It's possible to use an internal 32 kHz RC oscillator, which is an LSI, low speed internal, or an external high speed oscillator, which is the HSE, or high speed external, or an external low speed oscillator, the LSE, low speed external. The latter solution can be found on the development board, where the oscillator frequency is 32,768 kHz, which is the 15th power of 2. This is important because it can be used to produce a very precise unit of time, 1 second, which the microcontroller can do by dividing the oscillator's frequency 15 times by 2 to get 1 Hz. To set the RTC signal is as follows. Under clock configuration, you have the option to select the source of the RTC clock signal. As already mentioned, we will now select the LSE clock input, since the oscillator on the panel will provide the clock signal to the RTC. Now, let's take a look at the schematics of the development board. The oscillator should be connected to legs 8, input, and 9, output, of the microcontroller. At the same time, these are also the legs 14 and 15 of the port C, so they are referred to as PC14 and PC15 in the schematic. The responsibility of the C35 and C36 capacitors is to ensure the stability of the frequency, the theoretical value of which is given by the oscillator's manufacturer. The accuracy largely depends on the quality of the components used.
For capacitors, it is advisable to use first-class ceramic capacitors with the lowest possible temperature dependence, which are usually designated as NP0 or C0G. Accuracy is also important for quartz crystals, which are measured in ppm/Celsius degree, where ppm stands for parts per million. 1 ppm per Celsius degree means that the temperature change of 1 Celsius degree will cause the frequency to change by 1 part per million compared to the reference temperature of 25 Celsius degree. For more information on the crystals and their wiring, see Chapter 5.3.8 of the microcontroller datasheet and the AN2867 application guide. With this little insight, we are closing this video. We say farewell for now, but join us in the next part where we will show you how you can use the RTC's different functions in your program. See you there.
Bye bye.